Assalamualaikum dan salam sejahtera. Today we're going to learn about chapter 9, which is quantization of light. Quantization of light can be divided into two major subtopics. The first one is Planck quantum theory and second one is photoelectric effect. Planck quantum theory. At the end of this topic, students should be able to state Planck quantum theory, distinguish between Planck quantum theory and classical theory of energy, and last one is use Einstein equation for a photon energy. Assumption made by Planck in his theory are: number one, the EM radiation emitted by the black body is in discrete or separate packet of energy. Number two, each packet is called a quantum of energy. This means the energy of EM radiation is quantized. Number 3, the energy size of the radiation depends on its frequency. Now look comparison between classical theory and quantum theory. For classical theory, number 1, energy of EM radiation is continuously, while for quantum theory, energy of EM radiation is quantized or discrete. Comparison number 2, energy of EM radiation depends on the intensity of the wave. It's independent of frequency. While for quantum theory, energy of EM radiation depends on its frequency. Okay class, let's answer together quiz number 1. Here are the assumptions of the Planck quantum theory. Accept A. The EM radiation emitted by the black body is in discrete or separate packet of energy. B. Energy of EM radiation is quantized. C. Energy of EM radiation is continuously. And D. Energy of EM radiation depends on its frequency. Okay class, what is the answer? The answer is C. Energy of EM radiation is continuously.
Chapter 9.2 Quantization of light. At the end of this chapter, students should be able to define photoelectric effect, explain the phenomenon of photoelectric effect by sketching the diagram of photoelectric effect experimental setup, define threshold frequency, work function, and stopping potential, explain the failure of classical theory to justify the photoelectric effect, analyze by using graph and equation the observations of photoelectric effect experiment in terms of the dependence of kinetic energy of photoelectron on the frequency of light, half mv max square equals EVS equals HF minus HF naught, photoelectric current on intensity of incident light, work function and threshold frequency on the types of metal surface, W0 equals HF naught, use Einstein photoelectric equation, Kmax equals EVS equals HF minus W0. The photoelectric effect. The photoelectric effect is defined as the emission of electrons from the surface of a metal when the EM radiation or light of higher frequency strikes its surface. EM radiation or light strike the metal surface, and electron will be emitted. This electron, we call it as photoelectron. Photoelectron is defined as an electron emitted from the surface of the metal when the EM radiation or light strikes its surface. Photoelectric experiment. Cathode, anode, galvanometer, voltmeter, rheostat, and power supply. Explanation of the experiment. When a monochromatic light of suitable frequency or wavelength shines on the cathode, photoelectrons are emitted. These photoelectrons are attracted to the anode and give rise to the photoelectric current or photocurrent I, which is measured by the galvanometer. When the positive voltage or potential difference across the cathode and anode is increased, more photoelectrons reach the anode, thus the photoelectric current increases. Reversing power supply terminal. As the potential of the anode becomes more negative, less photoelectrons reach the anode, thus the photoelectric current drops until its value equals 0. This electric potential at this moment is called stopping potential. Stopping potential is defined as the minimum value of negative voltage when there are no photoelectrons reaching the anode. Einstein's theory of photoelectric effect. A photon is a packet of electromagnetic radiation with particle-like characteristics and carries the energy E given by E equals to hf. E is the energy of electromagnetic radiation, h is the Planck constant, f is the frequency of electromagnetic radiation. The photoelectric effects. Work function W0 of a metal is defined as the minimum energy of electromagnetic radiation required to emit an electron from the surface of the metal. Work function W0 equals to E minimum of the EM radiation. When the EM radiation strikes the metal surface, an electron emitted from the surface of the metal. Threshold frequency F0 is defined as the minimum frequency of electromagnetic radiation required to emit an electron from the surface of the metal. Work function equals to energy minimum of the EM radiation. E minimum equals to H F0. F0 is the threshold frequency. Case 1. Energy of the EM radiation equals to the maximum kinetic energy of electron plus work function of the metal. When the energy of the EM radiation is bigger than work function of the metal, electron is emitted with maximum kinetic energy. Case 2. Energy of the EM radiation equals to work function of the metal. Electron is emitted but maximum kinetic energy is 0. Case 3. Energy of EM radiation is below than work function. No electron emitted from the surface of the metal. Variation of photoelectric current with voltage. Different intensity but its frequency is fixed. Different frequencies but its intensity is fixed. Different methods of cathode but the intensity is fixed. Material 1, Material 2, Material 3. The work function of Material 3 is bigger than work function of Material 2, and the work function of Material 2 is bigger than work function of Material 1. Failure of wave theory of light. Classical prediction, photoelectric experimental observation, and modern theory explanation about photoelectric experiment. Experimental observation. Emission of photoelectrons occur only when frequency of the light exceeds the certain frequency, which value is characteristic of material being illuminated. Classical predictions. Emission of photoelectrons occur for all frequency of light. Energy of light is independent of frequency. Modern theory. When the light frequency is greater than threshold frequency, a higher rate of photon striking the metal surface results in a higher rate of photoelectron emitted. If it is less than threshold frequency, no photoelectrons are emitted. Hence, the emission of photoelectron depends on the light frequency. Experimental observation. Very low intensity but high frequency radiation could emit photoelectron. The maximum kinetic energy of photoelectron is independent of light intensity. Classical predictions. The higher the intensity, the greater the energy imparted to the metal surface for emission of photoelectrons. When the intensity is low, the energy of the radiation is too small for emission of electron. Modern theory. The intensity of light is the number of photons radiated per unit time on a unit surface area. Based on the Einstein photoelectric equation, Kmax equal HF minus work function W0. The maximum kinetic energy of photoelectron depends only on the light frequency and the work function. If the light intensity is double, the number of electrons emitted also double, but the maximum kinetic energy remains unchanged. Experimental observation. Photoelectrons are emitted from the surface of the metal almost instantaneously after the surface is illuminated, even at very low light intensity. Classical prediction. Light energy is spread over the wavefront. The amount of energy incident on any electron is small. An electron must gather sufficient energy before emission. Hence, there is time interval between absorption of light energy and emission. Time interval increases if the light intensity is low. Modern theory. The transfer of photons energy to an electron is instantaneous as its energy is absorbed in its entirely, much like a particle-to-particle collision. The emission of photoelectron is immediate and no time interval between absorption of light energy and emission.